folks, welcome to our second help video over the written portion of 8-20, the test premiere. We are picking back up with question number 6, where we had to write and balance chemical equations. On the second one, we also have a decomposition reaction. If you remember, we had several decomposition reactions that you were told you would need to know when we started this unit long ago. And in this one, we're talking about the decomposition of the carbonate ion, a metallic carbonate. The specific metallic carbonate we're talking about is magnesium carbonate. So over here, we need to write the formula for magnesium carbonate. In a decomposition reaction, we start with one reactant, and it falls apart into multiple products. Magnesium is 2+. It's in the alkaline earth metal family, Roman 2, group 2. They all have 2 valence electrons, so when they chemically react, they lose those 2 valence electrons. We also learned in our study of the polyatomic ions that the carbonate ion is 2-. So we crisscross a 2 and a 2, which is reduced to a 1 and a 1. This is thermal decomposition, so we would need to add heat to make this reaction happen. So what happens in the decomposition of the carbonate ion? Well, this is a reaction where one of the oxygens will stay. One of the oxygens will stay with the metal. We have 3 oxygens that are in carbonate ion. One of them stays with the metal. The other 2, if we take one away, we would have 2 left. The other 2 leave with the carbon in the form of carbon dioxide. That's what happens when the carbonate ions decompose. Now, how do they know that? Well, there's a couple ways they could tell this. When this reaction, if you put magnesium carbonate in a test tube and you begin heating it aggressively, and if you stick a burner splint into that test tube, that splint will go out. Why is that? Carbon dioxide, you know, is used in fire extinguishers. It will burn the splint out. The second test is called the lime water test. The lime water. If you bubble the carbon dioxide being produced in the decomposition of the carbonate ion, that carbon dioxide will go into the lime water. The CO2 will react with the substances in lime water to form a solid precipitant. It will turn white as this solid precipitates out a solution. That's the second test. If it turns lime water cloudy, you know carbon dioxide was produced. Now, let's take a look at where they get the formula for magnesium oxide. When that oxygen stays with the magnesium, we know the oxide ion is 2-. Magnesium is always 2+, crisscross reduce. We end up with MgO. We have 1 oxygen there, 2 there for a total of 3. We have 1 carbon here, 1 carbon here, 1 magnesium here, 1 magnesium here. It is balanced. We move on to reaction number 7. Zinc metal being dropped into aqueous hydrochloric acid. They're telling you it's fizzing and bubbling. And if you collect that gas that's released and you insert a burning splint into there, you hear an explosion, a loud pop, a barking sound. You see that gas igniting. That gas would be hydrogen. Hydrogen burns. We know that all the way back to the Hindenburg, which was filled, a Zeppelin that was filled with hydrogen gas. This is going to be a single displacement reaction. They didn't really tell us that, but aqueous hydrochloric acid, that is one of our strong acids, one of our 6 strong acids. Where do they get the formula for hydrochloric? Hydro is telling you that it is a binary acid. Hydro is the key prefix to tell you it's binary. So when it's a binary acid, chloric would be chloride, and as an acid, acids always have a hydrogen out front. The chloride ion here, chlorine, is in family 7. It is a halogen. They have family 7, has 7 valence electrons. They need 1 more to get 8. So they want to become 1-. The hydrogen ion that breaks off is going to be 1+, crisscross, 1 and 1. It's HCl. This is one of the many single displacement reactions that we had to take a look at. Zinc is an active metal, and it will displace hydrogen. The metal will displace the first element in that compound or replace it. It's a single displacement or replacement. So the green zinc is going to displace that red H and join up with the chlorides. Where do the H's go? Well, zinc is forcing. Zinc is an active metal. It's forcing the H pluses to take electrons. They each take one. They need two, so they join up. Each of the hydrogens breaking off, the H pluses end up with one of zinc's electrons. They join up to make the diatomic hydrogen. H2 is one of our diatomic elements. Where do we get ZnCl2? Well, zinc is 2 plus. It's a metal that is always 2 plus. If you look on many of your periodic tables, there's a Roman 2 above zinc's column. Remember, they're the S2D10 group there, group 12 in the transition metals. They have that Roman 2 above them because they lose those 2 electrons out of the S. Crisscross the 1 and the 2. The chlorides are always 1. Crisscross, we get ZnCl2. We have 2 chlorines or 2 chlorides. We have 2 hydrogens. We need a 2 out in front. Here comes another one of the decomposition reactions that we were asked to learn in number 8. You needed to learn the pattern for the decomposition of a metallic hydroxide. In this case, our metal is barium. Barium hydroxide. Hydroxide ion we learned is 1 minus. Barium's 2 plus. We're going to crisscross our charges. Barium's an alkaline earth metal, group 2. They have 2 valence electrons. They become 2 plus. The hydroxide ion's 1 minus. Crisscross, Ba parentheses OH parentheses 2 times. It's a thermal decomposition, so we need a plus delta H above that arrow, saying that we have to add heat energy. What happens when the hydroxide ion undergoes decomposition? Well, we have 2 hydroxide ions here. There's one of them, there's 2 of them. When these decompose, one of the O's will stay with the barium. One of the O's will stay 2 minus. It'll stay as a 2 minus. It'll pull off hydrogen's electron, leaving this H as a plus. It'll join up with this particular barium, and we end up with BaO. Where do we get BaO? Ba is 2, but we learned already that the barium is 2 plus. The hydroxide or oxygen, family 6, always 2 minus. Crisscross the 2 and 2 and reduce, we get BaO. The hydrogen that was left behind when this oxygen broke off of it to stay with the barium, where's this H plus going to go? It's going to join up with the other OH. So this initial O that broke off, OH is minus, so the O had 1 minus. It ripped the hydrogen's electron off to become 2 minus. There it is, 2 minus. So this H is now 1 plus. It's going to join with an OH minus. An H plus joining with an OH minus, that's water. Water's an H plus and an OH minus. The plus and minus cancel. It's left neutral. Let's take a look at balancing this thing. 2 hydrogens here. There's 2 there. There's 1 oxygen. There's 1 oxygen. We have 2 oxygens on this side. 2 oxygens right here. We have 1 barium there. There it is. This equation is balanced. We move on to the next page. We're going to start this next page. I doubt we'll finish it on this video, so you may have to watch part of this video and the next video, our third video on this, to get all the way through this. But here we go. Single displacement reaction occurs when a solid aluminum metal is placed in aqueous copper 2 chloride. They're telling us it's a single displacement or single replacement reaction. That means that they're telling us that the aluminum is more active than the copper metal, and it is. So first we have to write our solid aluminum. There's aluminum. It's solid. We're dropping that in aqueous copper 2 chloride. There's aqueous. Copper 2 is telling us that that copper's 2 plus. We know the chloride ion, as we've talked about a lot already, is 1 minus. Chloride is a halogen. The chlorines are in the halogen family, Roman 7, group 17. Roman 7 needs one more to get 8. They start with 7 valence electrons. They need one more to get 8. When they told us copper 2, they told us that the coppers are going to lose 2. So we crisscross the numbers. The 2 goes down there. The 1 goes down here. They told us it's single displacement or replacement. That's telling us that this aluminum is going to replace or take the place of that copper. So this green aluminum is going to end up with the red chlorine. Metals replace metals. Non-metals replace non-metals. So this aluminum is going to replace it, the blue copper, and end up with the chlorine or the chlorides. Aluminum is in Roman 3, group 13. Aluminum is famous. It starts with 3 valence electrons, 1 in the S, or 2 in the S, 1 in the P, for a total of 3. The chlorides, as we already mentioned, will always be 1 minus, crisscross. That 3 drops down there. That 1 goes here. What happened to the coppers? They were 2 plus, but they were displaced. There they are. They're going to precipitate out of solution. What's happening here is the aluminum is more active. It's going to force the coppers to take their electrons. We have 3 coppers at 2 plus. 3 times 2 plus is 6. So they can take a total of 6 electrons. Each aluminum is going to dump off 3. So we need 2 aluminums, each dumping off 3. 2 times 3 plus is 6 plus. So those 3 2 plus coppers all ended up with 2 electrons. They went from 2 plus back to neutral. As soon as they become neutral, they lose their plus. They lose their ability to stay in water. Water can hold on to ions because water has partial charges to it. The oxygen, as you remember, is strong on a water molecule, and it becomes partial minus. That partial minus oxygen on a water molecule can hold those positive ions, such as Al3 plus, or over here Cu2 plus. They can hold them in water, but as soon as they lose their charge, they lose their ability for water to hold them. They precipitate out of solution. That's why there's an S there. Now they want us to write this in ionic form. Number 10, write this equation in ionic form. All right, ionic form just means pull apart the ions. Well, this isn't an ion, so we don't have to pull it apart. Right here, these are ions. We have 2 pluses joining together with the 1 minuses. We pull them apart. We have 3 Cu2 pluses. We have 2 times 3. 2 times 3, we have 6 Cl minuses. Aqueous means that water has pulled them apart. So pull them apart. 3 times coppers, all 2 plus. We have 3 times 2, that's 6 Cl minuses floating around in solution. Over here, there's our 3 coppers. Boom. But they're no longer charged. We still write them in an ionic form. Ionic form, though, just means we're pulling apart the aqueous solutions. So we have 2 Al3 pluses. There they are. We still have 2 times 3 is 6. We still have 6 Cl1 minuses. There they are. That's the equation written in ionic form. In the next video, we'll show you how you can get the net ionic equation out of this. Hopefully these help videos are offering you some help here. The third video will pick up with number 11. If you have questions that are not being answered in these help videos, do not hesitate to email me. We'll be glad to set up a meeting with you or email back and forth so that you understand. Thank you for watching.